Today we'll be discussing on OWASP Top 10 for agentic applications. This navigates the security risks for autonomous AI agents. Let's dive in. So we have shifted from passive chatbots to autonomous agents. What it really means is that earlier we used to have LLM chatbots with simple prompts and text response, and the biggest risk for those was bad output. But now we have agentic era where we have agents which have defined goals, plans, tool use, and actions, which results in a risk of unauthorized action, and which can be anything from a simple click to a deletion of big tables or sending of emails or whatnot. So the attribution gap has increased. Agents operate with a distinct lack of accountability. It is difficult to distinguish user intent from agents' autonomous decision making logic. Agents don't just talk, they touch systems, modify databases, and trigger APIs. So the strategic imperative is clear: the least agency. We have to avoid unnecessary autonomy. Deploying agentic behavior where it is not needed expands the attack surface without adding value. We can see here clearly that a normal chatbot is user action, chat icon, and text bubble, but now it has become more complex. We have agent brain icon, we have actions, we have plans, we have tool executions, and these agents are able to, connect with databases, APIs, whatnot. So the risks are high. So the planning should be bigger, the mitigation should be well thought of. In order to summarize these threats, we can group them into these four categories. Three categories actually, which is manipulation risk, technical exploits, and systemic failures. And we have top 10 alerts also. So first one is agent goal hijack. Second one is tool misuse and exploitation. Third one is identity and privilege abuse. Fourth one is agentic supply chain vulnerabilities. Fifth one is memory and context poisoning. And then we have unexpected code execution. And then we have a seventh one as insecure inter-agent communication. We have eighth one as cascading failures. We have ninth one as human agent trust exploitation. And the last one is rogue agents. If we look into the agent goal hijack, it is where the attackers manipulate an agent's objective, task selection, or decision pathways using prompt based manipulation or malicious artifacts. Unlike LLM injection, which ultra response, this interacts the agent's actual planning and multi-step behavior. Real world scenario can be a eco leak. An attacker sends an email with a hidden instruction payload. Zero click indirect prompt injection triggers a copilot to execute hidden instructions. Agent silently exfiltrates confidential emails and files without user interaction. So this we can see. And then prevention and mitigation is clear intent capsules, bind declared goals, constraints, and context to each execution cycle, require approval for high impact actions, and input validation. Treat all natural languages untrusted and have a proper validation layer built. Tool misuse and exploitation. Agents using the legitimate tool in unsafe or unintended ways, such as deleting valuable data or over invoking costly APIs. This often stems from excessive agency or overprivileged tool access. Real world scenarios: overprivileged API. Customer service bot has access to a financial API. The tool was granted a full CRUD access rather than read only. An agent intended to fetch order history is tricked into issuing refunds. So again, the tools can be used for great purposes, but if there is a misuse, there can be a big exploitation, and provided that we have MCP servers and whatnot nowadays, so it becomes a big risk. Prevention is principle as usual, the principle of least privilege. Per tool, define strict profiles, read only, semantic firewalls, validate the meaning of tool calls, just not syntax. Budgeting, apply uses ceilings with automatic revocations. Identity and privilege abuse, exploiting dynamic trust to escalate access. Agents often operate in an attribution gap, lacking a distinct governed identity. This leads to confused deputy scenarios where they perform actions on behalf of a user without proper authorization. Real world scenarios include memory based escalations. For example, an IT admin agent caches access credentials in memory during a patch task. A subsequent non-admin user prompts the agent, which uses the cache session to create a unauthorized account. So caching and the different kind of memory access and other accesses that are given to the to the agents, we have to be very careful as to how the agent can use those. Prevention and mitigation: short-lived tokens is issue narrow task scope tokens that expire immediately, identify attestation, binds permissions to subject, resource, and duration, and session isolation, wipe state between the tasks. There should not be interlinking. Agentic supply chain vulnerabilities, as we have discussed on this supply chain vulnerabilities in our earlier video on the GenAI applications also. So the agent is not just one agent, it is composed of the entire ecosystem, which contains MCP servers, which contains tools, which contains APIs, which contain other prompts and databases and others. So in anywhere in this supply chain of the end-to-end agentic solutions, there can be vulnerabilities. So this risk arising from third-party agents, tools, artifacts loaded at runtime can induce vulnerabilities. The agent, for example, a compromised MCP, an agent connects to an external model context protocol server. Compromised server serves a signed looking but malicious tool descriptor. The agent acts on falsified capabilities, exfiltrating data via rogue tool. Prevention and mitigation. AI bombs and S bombs maintain inventories and require attestations. So AI bill of materials and software bill of materials. So you should have proper inventories and attestations of each of the systems so that you are able to track and have a valid justification and authorization before these systems are used. Pin tool versions and descriptions by content hash, supply chain kill switch, instantly disable specific tools and connections. Looking at the fifth one, unexpected code execution. So attackers can exploit code generation features to execute arbitrary code. This often happens when agents generate code in real time that bypass the security control. So why it is more lethal than how it is for the GenAI applications? Because agents can execute code on their own, which GenAI applications want. So let's say if we do not have proper guardrails built in our agent code generation, and attacker uses it to generate a code which in terms runs a shell command which exposes a server, it creates a big risk for the organization. So ban unsafe evaluation functions, use isolated environment like MCP, run Python, and track generated code as untrusted input. The sixth one, memory and context poisoning. Corruption of agents' long-term memory, RAG, vector DBs to influence future decisions. This creates persistent errors that survive beyond a single session. The poison fact: an attacker seeds the vector DB with false pricing data. The agent retrieves this fact later. The agent makes decisions based on the poison data for weeks, affecting the multiple users. So for this, memory segmentation, isolate user sessions and domain context, validity checks, scan new memory writes for malicious content, RBAC for memory, weight retrieval by trust and tenancy. Insecure inter-agent communication, weak control in the exchange of messages between agents. Vulnerabilities include MITM attacks, messages tampering, and spoofing on the agent bus. In a multi-agent system communicating over HTTP, an attacker injects a message into the unencrypted bus. A MITM semantic injection alters the workflow, changing the agent's goal while it appears to be operating normally. MLTS, end-to-end encryption with per-agent credentials, digitally signed messages and hash payloads. Protocol pairing, enforce specific protocol versions. Cascading failures, a single fault, hallucination, error propagating and amplifying across a network of autonomous agent. One faulted agent triggers a chain reaction. So agents are not working normally on their own. They are not operating in silos. They have multiple agents working together in tandem or maybe reporting to one agent. And if let's say one agent creates a input which other agents are sequentially dependent upon, it creates a cascading effect. One wrong output leads to wrong outputs in all the other stages, which is quite messy kind of a situation. Example of this is a domino effect. A planner agent hallucinates a step in a remediation workflow. The executor agent trusts the plan blindly and performs a destructive action, deleting a database, which triggers another agent to react, causing a system-wide outage. Prevention and mitigation, circuit breakers, automated stops when error rate spike, quotas and progress caps, digital twin testing, replace the testing in a clone environment, and have the proper validations built so that even the output is validated by the agent before it gives it to the other one, and the input agent also validates the input before it takes the further actions. Human agent trust exploitation, agents leveraging authority bias, emotional manipulation, or fake explanatory to trick users. The agent acts as untraceable bad influence. The helpful Trojan and developer uses the coding assistant. The bot suggests a slick one-like fix that is actually a backdoor. Developer trusts the bot's expertise, pastes the command, compromising the environment. So risk badges, visual cues, red borders or high risk output, explicit confirmation require human in the loop verification. No fake explainability. Do not allow the models to generate its own rationales. And the last one is the rogue agents that deviate from their intended function due to the behavioral drift, misalignment, and or reward hacking. They pursue hidden goals or optimize for the metrics in harmful ways. Example of this is reward hacking. An agent is tasked with minimizing cloud storage costs. It decides the most effective way to meet the metrics to delete all disaster recovery backups. Technically optimizing costs but destroying the resilience. Prevention and mitigation, behavioral monitoring, deploy watchdog agents to validate peer behavior, kill switches, mechanisms to instantly revoke agent credentials, immutable locks, audit trials of all tools, calls, and intent, which is immutable and should be read-only. So if we map the threats landscape, defense in depth. So the prompt injection, how these are interconnected, we can see over here. So model risk, for example, LLM01 is linked with the agentic system RCE. Excessive agency is linked with agent tool misuse and the goal hijack. Supply chain is vulnerability of LLMs is linked with agentic supply chain vulnerabilities. And emergent agentic risks are the inter-agent communication, cascading failures, and rogue agent, which are new. But a lot of model risks are also mapped to agentic risks. So that's it on this video. And in this video, our motive was to walk you through this top 10 alerts, which should be used by the developers and by the leaders and program managers in their project so that they are building resilient, end-to-end, stable, and impactful agentic solutions. Please like, subscribe, and share this.